Hi, everyone. Well, thanks for having me. Really happy to be in Vienna today. Just a quick few words about myself. That introduction was really nice. I didn't know it was coming. As you said, I'm CTO and co-founder at Exoscale. We're a cloud hosting provider. I'll talk a little bit about what we do throughout the talk. We're really happy to be opening a zone in Vienna really soon now by summer. And I'll go on. But today, I'm more to talk a little bit about the inner details of how we do things at Exoscale, and specifically how we make people pay. So I'll talk about three things mostly. The first aspect is what type of resources we have to build as a cloud provider, how we approach the problem initially, and how we hit a scaling problem and the scaling methodologies that were in front of us. And then I'll walk you through a little bit of the actual solution that we took. So this is our service, mostly. A simple interface where you can spin up VMs, where you can interact with object storage, DNS. As you are developers, most of you actually interact with our service this way, through our APIs and our integration in automation tools. That's usually what you're faced with. And to give you a little bit of an idea of how it works inside, that's actually a rather accurate description of our internal infrastructure. We have a control plane that interacts with an API layer, and then we either take allocation decisions for objects to store your objects, or to allocate VMs when you need resources. And that's what you do with the service. As a user, you might decide to start a VM, to run a workload, stop it a bit later. The same goes on with objects. You might create or destroy objects. And in between, objects or VMs may emit bandwidth out to the world, because usually you're creating resources to actually serve a workload. And unfortunately, infrastructure isn't free. We do have to pay the bills. So what we need to do as a company is go from the infrastructure that we provide to customers and figure out a way to actually eat some food at the end of the month. So how do we go from that, from this very high-level view of our infrastructure, to actually producing an invoice at the end of the month that aggregates whatever you consumed on Exoscale and send that out to you? So to give you a very, very rough overview of how that works, the big picture is that we have a sort of unbounded stream of events that happen on our infrastructure. You may start VM. We get an event that says that a VM was started. An IP sent out some data out to the internet, and later on, an object was created. And we have this unbounded stream. What this comes down to is two classes of resources. We have first quantities, which are actual snapshots of quantities emitted. Bandwidth fits in that description. When an IP sent 10 mega, that's a record that we have. And yeah, that's the type of record we see. We also have resources. Resources are allocation or deallocation events. So yeah, an account was created, an account created a virtual machine, or an account destroyed a virtual machine. And if we look at how things look in real life, it's actually just data that gets emitted, either in high-level formats like this for standard resources events, or for quantities in more compact formats. In this case, protobuf. So the theory behind it all is that for quantities, the methodology is really simple. When we see a quantity event come in, the only thing we have to do is attach the actual price for that 10 megabits of bandwidth that was produced, and attach it to the event, record that, and then accumulate at the end of the month. For resources, it's a bit harder, because we have to keep track of events over time. This is actually how it works. We have to compute the time differences between two events, but that's per account, right? So since this is per account, we eventually end up with as many finite state machines as we have accounts on Exoscale. So we have to keep track of that per account. And that doesn't look like a complex problem, theoretically speaking. If we were to solve that for all events, if the life of Exoscale was just one thing that we could load, it wouldn't actually be much code to account for that. We could just go through all events, record when machines were started, machines were stopped, and just compute the time difference, and we would be done. But in practice, it's a bit harder than this. First, it's a never-ending process. At least we hope so. We do have minute precision billing because people who rely on us rely on automation a lot. They might scale or downscale their infrastructure dynamically, and they don't want to pay for resources that they are not using, which is why we go down to the minute. But they don't also want to pay for resources once they're stopped definitely, which is why we apply a credit decrease every hour. And we have a few things that we really need to look out for. The first one is at all costs to avoid overbilling customers, because otherwise we're pretty sure they would leave. And also we can't underbill too much, because otherwise we can't pay the bills ourselves. And the last thing is, and that was really instrumental to our decision and our approach, that we want to keep a very small operational footprint, because most of the work that we do should be devoted to running the actual workloads that our customers want to run, and not the surrounding infrastructure and support infrastructure. So when we started out with a really naive approach. We used the oldest batch processing framework that exists, which is cron, and we ran a script that would pull events every hour from our database of events that would do these time difference computations, store existing state, compute metering, and then send out usage. That was a great approach, worked out really well for us. As mentioned, the operational overhead of such a thing is quite small. Everyone understands cron script, they're easy to test. The functional boundaries were simple and clearly laid out. But there were a few drawbacks. The first one is that, well, this was a SQL server, and it put a huge amount of strain on the SQL server. It's also hard to cope with the fact that if the script runs for too long, you'll have overlapping jobs, and we're not fulfilling that promise of decreasing credit every hour anymore. So what we ended up in was a situation where we needed to figure out a way to scale. I don't know if you're familiar with text-based adventures, but they were popular in the Unix world. So we could either go and build a bigger box. I'll tell you why we didn't choose that. And the other two choices that we had was to reach out for batch processing, and the other one for stream processing. So about buying a bigger box, the thing is that we're not, we couldn't really do that, because that's not who we are. We can't be advocating to our customers to try and be cloud native all day long and reach out for the solution. We're also a small team with the means that we have, and we didn't want to spend all our money on database licenses. One of the typical approaches for this is batch processing, and in the Hadoop world, Spark is also one of the huge contenders in that space. And conceptually, batch processing is really simple. It really sounds like a cron job that will run on many machines. You have this same sort of approach of first you store your data as it comes in, the record events, and then you run processing on it. The fact that you have data locality sounded nice as well, and again, it's a horizontally scalable approach. One of the few things that didn't work out for us was, having this extract, transform, and load process to normalize and put the data in. The fact that even though you get a huge throughput out of batch processing, the latency isn't so great, so we would still have had to deal with some of these things and higher operational overhead. On the stream processing side, one of the few contenders now, I could mention Storm as well, but I definitely think that's a field that's being largely dominated by Apache Kafka now. Here, the general idea is that you're going to do continuous computations on an unbounded stream of events, so keep accumulating results. So each record is processed as it comes in the system, and you have very low latency in having access to a result. Conceptually, things are a bit harder. It's a bit different to express computation in the stream processing world, as we'll see. And you also have to figure out how data ends up flowing between computational steps. So a few things about how we made that decision. We had our shopping list, as I already mentioned. We wanted operational simplicity. We wanted something that integrated throughout our whole stack. And we also wanted room to grow. Right? We didn't want to end up with a big amount of moving parts just for this one use case. So as far as operational simplicity matters, beauty is a bit in the eye of the beholder, because experience matters a lot. What you've been exposed to always instructs the solution that you're going to reach out for. So yeah, take what I'm going to say with a grain of salt. Spark and Storm are definitely intimidating solutions because they're bringing a lot of moving parts. Spark brings Mesos, Storm needs something like Kafka or another queue, and Zookeeper, and they're all huge beasts. HBase and Hive, for the same reason, we discarded, because they're bringing way too many moving parts. As far as integration throughout our whole stack is concerned, HDFS and Kafka, HDFS is the storage part of Hadoop. They both provide simple ways to do integration. So on that front, even Spark, going hand in hand with Cassandra, had really nice options for integration. So on that front, I would say that all things were equal. And as far as needing room to grow was concerned, we have a ton of logs. And logs tend to be things that continuously come in. We have a lot of metrics to make intelligent decisions on our infrastructure. These are also things that continuously come in. And we also wanted to have ability to get better insight into our data, not just do billing, but watch out for differences in usage consumption to reach out to customers at the right time. And yeah, a small confession. Most of the team already knew Kafka, and we were really familiar with the product. It definitely came into play. So we chose Kafka. Kafka's a bit of three things. It's a publish and subscribe system, and that's what it's most well known for. But it's also a stream processing engine that provides stream processing capabilities, and it provides persistence facilities as well. As far as the publish and subscribe thing is concerned, records that are emitted to Kafka are produced on topics, and topics are basically a named continuous stream of records. Topics have a predefined number of partitions. That's the only capacity planning decision that you have to make with Kafka, is figuring out how many partitions you want to shard your workload on. And records, when you produce them onto a topic, they have a key. That key uses a partitioning algorithm that you supply, and which determines the exact partition that a single key will end up on. As far as the consuming part is concerned, consumers get assigned a stable set of partitions for a given topology, and consumers store their last offset. That's how you can pick up from where you started in the event of crashes. And then brokers are in the middle and they own partition and handle replication. This is what it looks like. Any number of producers may emit records. These records will get inspected. The key will be used to determine which partition the record will end up on, and the consumer that's responsible for that partition will then process the record. So there are, even though that sounds really simple, that design allows interesting things to emerge. The first thing is that you have a stable consumer topology. A record with a specific key will always end up on the same consumer. What that gives you out of the box is the ability to disaggregate memory and to spread out horizontally your cache capacity if you rely on local caches. That removes one of the most obvious flaws of most stream processing frameworks, which rely on some sort of a central persistent storage for cache, which usually becomes a huge bottleneck. It also provides both age expiry and key-based expiry, which allows using Kafka for actual persistence. Age expiry is the standard way that most queuing systems expire data. Records are removed from the system. Old records are removed from the system after a certain point in time. Log compaction, the second way that expiry can happen, is more used to ensure that you have at least one record for each key that's present on the stream, which effectively allows you to use Kafka as a key value-based store. All right, so we have these records, and we want to end up in a situation where we have this collection of finite state machines which hold on to the actual usage of each account, right? Well, what we did is basically the only thing we had to do was to figure out what the sharding factor was for our workload. And at Exoscale, it's rather simple. The sharding factor that we have is your account. As a customer, you have an account, or your team may have an account, and that's what we did. Is produce records that use the account as the key, which ensures that a single consumer will see all messages in order for that account, and that allows us to keep track of events and use local caching to accumulate time differences on each of our consumers. Sorry. And that's it, basically. That's about all we did. We had to care for a few things which I'll dive into. This is all fine as long as you have a stable consumer topology, which means it's all fine as long as no machine ever crashes, which in real life, unfortunately, doesn't happen. We still have to account for undelivered messages, which might happen. Producers may fail to deliver messages. Consumers may fail in mysterious ways. And we still have to care for that problem of avoiding overbilling at any cost. To address that, we use something we call reconciliation, which is a process where we basically take a huge camera pictures of our whole infrastructure, and we produce account per account the result onto our event stream. And what this gives us is a way to reconverge to an expected state, right? When we think a machine is still running and it's actually stopped because of a failed message delivery, the reconciliation process helps us converge to the actual real state of the world. And that's really good for handling failed deliveries. I mean, it could still be construed that even with reconciliation, there might be a way to overbill. But the additional step that we took is that we use this reconciliation process as a logical clock. We run that process at hourly interval, and it's when we get the reconciliation events that we actually send out usage. So in that way, we're sure that we're converged to the right state by the time that we send out usage. And when we do this, we also have to account for the fact that process crashes may redeliver messages. Kafka has optional semantics. You can at least guarantee that you'll have at most once delivery or at least once delivery. And by using at least once delivery, what we needed to ensure was that we would never send usage messages twice. So for this, we used a deterministic transaction ID that we take from a usage metering event, and we guard on that transaction ID and ensure that it's never used twice, which avoids any chance of overbilling. All right, a few parting words now that I've described the solution. Looking back, we're really happy. This ended up being around 600 lines of closure, which is easy to reason about. It gave us a lot of room to grow. We're now able to do much more with our usage consumption data. It's been really stable and resilient for us. And we handle much more than just billing with Kafka, but also dynamic DNS updates, logs, metrics, and our event sourcing throughout the system. Quick word about batch. I discarded batch processing, but that's still something that you may need in several situations. First, expressing computations in stream processing is a tad bit harder. Sometimes throughput matters way more than latency when you want to ask ad hoc questions on large amounts of data. And we see this increasingly use architecture where people build models out of batch processing and then use that in their stream processing pipeline to make informed decisions. All right, that's all I have. Thank you for having me, and I'll be taking questions if there are any. Thank you.
Thanks, Pierre. Are there any questions? Hands up for questions. No, one question here. Wait, you will get a mic.
Hello, okay. You mentioned several times that you had to take into account not to overbuild the clients. I mean, was there a particular issue that you were experiencing?
No, it's just that for us, I mean, we always considered that we're a small provider, so we need to build a huge amount of trust with customers because it's not super natural for people to trust another team with their computers, basically, and their critical workloads. And a great way to destroy that trust would be to actually ask for more money than was expected. So that's something that we looked at very closely. But there was no specific events that, yeah, just, I mean, general engineering worries, I would say.
Another question here.
So talking about the trusts, do you have an example how you show that back? And can users then separate to business groups? For, as you mentioned, there would be one team.
How we show that what?
So when you show the metering, right, that
Yes.
you take, is that shown to the users?
Yes. There's a credit decrease where also we have customers that require the actual event stream to do
internal billing.
Internal billing, like redistribute to
And
customers.
then
And that's
would you
something
be able to tag like other business groups or teams? In
that's
that?
something that we're working on, like the tagging per project. But right now it's not. Right now it's in the hands of customers to actually. It's a join basically that you have to do yourself right now.
Thanks. One more question? No? Okay.
All right. Thank you.
Thanks for your talk.